Welcome to Chapter 4, Selection Structure and Logical Operators. By the end of this chapter, you'll understand dual alternative and single alternative selection structures, use relational comparison operators like equals, less than, and greater than, apply the logical operators and, or, and not, make selections within specific ranges, understand precedence when combining operators, and learn the case structure. Quick refresher on the two selection types. Dual alternative always does one of two things. If you have a car, you drive to work. Else, you get fired for not showing up. Single alternative does something only if the condition is true, with no action otherwise. If it's dark, turn on the lights. If it isn't, nothing happens at all. That's the core distinction we'll build on throughout this chapter. Dual alternative selection has two possible outcomes: an if then else, where something always happens either way. If you have a car, then you drive to work. Else, you get fired for not showing up. If you have an umbrella, then you stay dry in the rain. Else, you get soaked and catch a cold. One branch or the other always executes. Here's dual alternative selection as actual code, in Java, C++, and Python. If age is 18 or older, the program prints that you can vote. The else branch prints that you cannot. The else guarantees one branch or the other always runs, no matter what age holds. Single alternative selection has only one possible outcome, an if-then with no else, so nothing happens if the condition is false. If it's dark, turn on the lights, otherwise no action is taken. If the homework is completed, submit it, otherwise nothing happens. The false case simply does nothing at all. Here's single alternative selection as actual code, in Java, C++, and Python. If the temperature is above a threshold, the program prints that it's hot outside. There's no else. If the condition is false, the program just moves on, taking no action. Two relational operators check for equality. Equals, written as a double equals sign, checks if a variable holds a specific value. If x equals 3, checks whether x is 3. Not equals, written as an exclamation equals or diamond bracket depending on the language, checks the opposite, whether x does not equal 3. Don't confuse the double equals comparison with the single equals assignment operator from earlier chapters. Greater than and greater than or equal to compare magnitude. Greater than, a single right angle bracket, checks if a variable's value exceeds another. If x is greater than 3 is true only when x holds more than 3. Greater than or equal to includes the boundary itself. If x is greater than or equal to 3 is true even when x equals exactly 3. These operators evaluate left to right. Less than and less than or equal to work the same way in reverse. Less than checks if a value falls below another. If x is less than 3 is true only when x holds fewer than 3. Less than or equal to includes the boundary. If x is less than or equal to 3 is true even when x equals exactly 3. Same left to right evaluation as the greater than operators. Three logical operators let you combine conditions. And, written as a double ampersand, requires all conditions to be true for the result to be true, checking that both x and y are positive, for example. Or, written as a double pipe, requires just one condition to be true. And not, a single exclamation point, flips a condition's Boolean value entirely, so a true becomes false, and vice versa. And requires every condition to be true before the result counts as true. Grocery shopping. If you have money and the store is open, you can buy groceries. Both have to hold, or you can't proceed. Studying for an exam. If you have your textbook and you're not tired, you can study effectively. Miss either one, and effective studying doesn't happen. And uses short-circuit evaluation. If the first condition is false, the second is never even checked, since the overall result is already guaranteed false. That's why it's smart to test your most likely false condition first. It saves unnecessary evaluation, and is ideal for enforcing multiple constraints at once, like checking that a user is logged in and has the right permissions before granting access. Here's and as actual code. In Java, C++, and Python, the program only prints that you can enter the club if age is 18 or older, and the person has a valid ID. Both conditions have to hold true together. Miss either one, and nothing prints. Or requires just one condition to be true for the result to be true. Choosing transportation. If you have a car or there's a bus available, you can get to work. Only one needs to hold. Deciding breakfast. If you have bread or cereal, you can eat. You don't need both. Either one alone is enough. Or also short circuits, but in the opposite direction from and. If the first condition is true, the second is never checked, since the overall result is already guaranteed true. That makes programs run faster by skipping unnecessary checks. Or is ideal for fallbacks and alternatives, like unlocking a door if the key is in your bag. Or your pocket, either location working just fine. Here's or as actual code, in Java, C++, and Python. The program prints that you can get to work if you have a car. Or a bike. Either one alone satisfies the condition, so only one needs to be true. Not flips a condition entirely. True becomes false, and false becomes true. Checking if a store is closed. If the store is not open, you stay home. The condition is reversed from how you'd normally think about it. Deciding on a movie. If it's not available on streaming, you rent a DVD. The action only happens when the negation holds true. Not has no short-circuit behavior. There's only ever one condition to evaluate, so there's nothing to skip. It's excellent for flipping a condition's truth value directly, like checking if is logged in is not true to detect someone who hasn't signed in yet. Not often pairs naturally with and or to build more complex logical expressions. Here's not as actual code. In Java, C++, and Python, the program checks if is logged in is not true, and if so, prints that the user isn't logged in. Not takes whatever Boolean value is logged in holds, and simply flips it before the condition is evaluated. Range checks come in two flavors. An inclusive check for comfortable temperature, 65 to 75 degrees inclusive, uses greater than or equal and less than or equal, so both boundary values count as comfortable. An exclusive check instead uses strict greater than and less than, so the boundary values themselves, 65 and 75, are excluded from the comfortable range entirely. Speed limits work the same way, just checking the outside of a range instead of the inside. An inclusive fine check, speed at or below 30 or at or above 60, means both 30 and 60 themselves trigger a ticket. An exclusive check instead only finds strictly below 30 or strictly above 60, meaning driving at exactly 30 or 60 stays legal and avoids the fine. To check a range, combine relational operators with and, so both a lower and upper bound get satisfied together. If x is greater than or equal to 10, and less than or equal to 20 checks whether x falls between 10 and 20 inclusive. This pattern works the same way whether you're writing C++, Java, or Python, just with slightly different syntax for the and keyword itself. You can write a range check as nested conditions, an outer if checking the lower bound, with an inner if checking the upper bound inside it, or as one combined condition using a and d. Here's the same range check, 10 to 20, written both ways in Java. Nesting works, but the combined version using and says the exact same thing in a single, cleaner line. Here's that same nested versus combined comparison in Python, and Python actually offers a third, even cleaner option. Chained comparison syntax, writing 10 less than or equal to x, less than or equal to 20 directly, checking both bounds in one natural reading expression that most other languages can't do this way. When combining multiple operators, precedence determines evaluation order. Parentheses always evaluate first, letting you group conditions and override the default order entirely. Not evaluates next, before and or or get applied. And between and or themselves, and evaluates first, unless parentheses say otherwise. So when in doubt, use parentheses to make your intended order explicit rather than relying on memorized precedence. Here's precedence demonstrated in Java, with A true, B false, and C true. Without parentheses, not A, evaluated first, gets OR'd with the result of B and C. Add parentheses around A or B instead, and not applies to that whole grouped expression before and C gets applied, producing a completely different result from the exact same three variables. Here's that identical precedence demonstration written in C++. Same two expressions, same A, B, and C values, same contrast between relying on default precedence versus using parentheses to force a specific evaluation order. The logic translates directly regardless of which language you're using. And here's the same precedence demonstration one more time in Python, using its plain English not, or, and keywords instead of symbols. The behavior is identical to Java and C++. Parentheses always override default precedence, no matter which language expresses the logic. Case and switch structures evaluate a single variable or expression, and run the block of code matching a predefined case, with the default block catching anything unmatched. A day-of-week program might output workday for Monday through Friday, weekend fun for Saturday, and relax for Sunday. A traffic light program maps red to stop, yellow to prepare to stop, and green to go. A restaurant menu maps each numbered option to its price. Here's all three scenarios: traffic light, restaurant menu, and day of week, written with Java's switch statement. Notice the day of week example stacks 5 case labels together with no break in between, letting Monday through Friday all fall through to the same workday output, while Saturday and Sunday each get their own distinct case. C++ handles these the same 3 ways, but notice the traffic light and day of week scenarios use if-else-if chains instead of switch, since C++'s switch statement works best with simple numeric or character values rather than strings. Only the numeric restaurant menu uses an actual switch here. Python takes a similar approach. If-elif chains handle the traffic light and day of week logic, since older Python versions have no built-in switch or case statement at all. For the restaurant menu, this code uses a dictionary lookup instead, mapping each option number directly to its price string, with a fallback message if the option doesn't exist. Before next class, build a logical puzzle using all 3 operators, and, or, and not, combined together. following the example format shown with variables x, y, and z. Bring it to class, ready to stump your classmates. If you manage to stump the entire class, you'll earn a bonus.